when you do that. So we're going to look at the bacterial growth curve. One axis is going to be time. Now this is going in hours because remember, most bacteria can replicate in 30 minutes, right? But depending on the species, I might need to plot out 2 weeks, I might need to plot out, 2 days. But we always plot the log number of cells. So here's your bacterial growth curve. In your bacterial growth curve, there's certain things that you need to know for your second test. First thing is, what is this growth curve? This is bacterial population growth. So it might be bacteria growing on that leftover piece of pumpkin pie in your refrigerator since last Thanksgiving. It might be bacteria growing in your patient. It might be bacteria growing in a culture in a broth test tube. It might be bacteria growing on a petri plate. You might be considering the entire petri plate, or you might be considering one colony on the petri plate. Those all might be considered populations or cultures of bacteria. This curve represents bacterial population growth on a finite medium. In other words, it's not utopia, it's real world. This curve, if it went up forever and ever and ever, that would be utopia. That would be bacterial growth with infinite resources, infinite space. Don't have to worry about accumulating waste. That's not realistic. It can't go on like that forever in the real world. So we're back to the real world curve. One thing I don't like about this curve is I would put a 0 here. And when you inoculate your bacterium, you can't start with 0, because 0 cells can't divide and make 2 cells. You have to start with at least 1 cell. And usually you don't know how many you're starting with. You can grow them and then work backwards and sort of get an estimate of how many you started with, but you probably don't know exactly how many you started with. So my point is, you can't start with 0. You have to start with some amount, even if it's 1, but probably it's not going to be 1 because they're so small. So this curve starts not at 0, but at some number of cells, okay? In our bacterial population growth curve, another thing that I don't like about it is I was always taught to put little arrows at the end of my axis, and they don't have them here. It's just the way I was taught. That would kind of bug me, but all right. So at this point, we're inoculating a new culture. So let's say Pasteur gets some bacteria from chicken poop, and he's able to isolate it into a pure culture. So he has just Yersinia multocida from the chicken poop, right? And he puts them into a petri plate or a tube of broth, right? So he inoculates his plate right here. Well, these bacteria came from chicken poop, where they had to earn a living by making the chicken sick. But when you put them in this artificial lab medium, it's a different environment for them. So they're going to probably not use the same enzymes for digesting poop as they're going to use for digesting nutrient agar. So they have to acclimate. So the lag phase is a period of acclimation for the bacteria. And while they're acclimating, notice there's no net change in bacterial numbers. Some bacteria might get it on the ball and divide, or they were getting ready to divide before we transferred them over, so they're ready to divide now. And others are going to take longer to acclimate and not start dividing till later. Some of them might be older when you put them in here and they die off. And some might not be able to acclimate and they die off. So you're going to have some replicating and some not replicating. But overall, there's no net change in bacterial numbers. to the new environment right now. It's the period of acclimation. Once everybody gets acclimated, then they're going to take off. Notice this part of the curve matches this. It's an exponential incline, an exponential increase in bacterial numbers, and that's called the log phase because it's logarithmic growth. This is what we call exponential or logarithmic growth. There we go, logarithmic. Maybe I got it right that time. Sometimes if I overthink stuff, I can't get it right. Like in exercise class, you're like, is my arm supposed to go that way, my leg go that way, or is it supposed to be this way? Can't overthink it. Okay, so the lag phase, these are called phases, by the way. Phases of the growth curve, of the bacterial growth curve. Lag phase, they acclimate. Log phase, they're acclimated. The environment is still fresh and new, right? Lots of space, lots of nutrients, not too many wastes accumulated yet. So they have a good opportunity to grow their very best. This is the healthiest time for a population. If you're a smart bacterium, you're going to make an inclusion now. You're like, I got plenty of food to eat, and there's plenty extra. I think I'm going to store some up as an inclusion. So cells would make inclusions at this time. Also, if you're running an experiment, you want to work with your bacteria while they're in their healthiest stage. If you want to do a gram stain, you want the most accurate result you can get, you want them when they're healthy, when their walls are sturdy, right? So this is the time to take them for experimentation or identification with a gram stain. If you wait too long, the reason I say this is because when I was a graduate student the first time in Ohio, I lived in Ohio, I went to Miami University in Oxford, Ohio, and I worked for a professor of parasitology and particularly protozoology. So we weren't growing bacteria, we were growing protozoa. But same idea with the protozoa. And so I didn't have a car because I was a poor graduate student. All I had was a bicycle. And you know how graduate school is, a little heavy partying goes on. You know, you steal the chemicals from the chemistry lab and you put them in the punch and all that kind of stuff. So I had a tendency to party sometimes, and I was supposed to go move my tetrahymena. You take them here when they're healthy and transfer them to a new tube of broth, and then they grow, and then you transfer them to a new tube of broth. If you wait too long, they're not going to be very healthy. So it's like you're starting a new population with a bunch of old people. That's not going to work. You have to get them when they're young, right? And I'd be partying too much, and then all of a sudden it's like, oh my God, it's been 2 days. I got to go switch over my tetrahymena. And I'd be like riding my bicycle with a hangover, have to go to the lab and do all that crap. I hate it. So, but if you wait too long, if I didn't go, if I slept off my hangover and didn't go, and I waited and I didn't take until stationary, or one time I even did it in the decline phase, and I still was able to get a few that could still replicate. But what's going to happen? My population's not going to grow to its best capacity, right? So this is why it's the best time to take them for experimentation or for maintaining your culture, for starting new cultures from it. Or I'll just put a lot of culture in it. Okay. The time you get to this part of the curve where the little cursor is, where the little arrow is, what's happening now is your population has grown. So think of the baby boomers, right? War's over, all the soldiers come home, they build a lot of houses, make a lot of babies, buy a lot of cars and TV sets and all that stuff, and these neighborhoods are getting crowded and the babies are growing up and there's people all over the place and there's waste all over the place. That's what's happening. The population is booming and gets to a point where it can't grow anymore because the environment doesn't have the resources to support it. So once you reach the stationary phase, if you want to have a baby, you're going to have to kill off grandpa. You know what I mean? Because there's just not room for both. So that's the idea. When you get to the stationary phase, some cells are still capable of replicating, and some cells are dying of old age. So, let's say a cell replicated here, it might die off by here. But a cell that just replicated here might have its second generation up here. So it's all relative. In the stationary phase, again, no net change in bacterial numbers. That's why the line is flat. So wherever you have a flat line in your curve, I've got more bacteria in my population there than I do here. But still, there's no net change. It's a flat line. And I've reached my carrying capacity, which is actually not a microbiology term, it's an ecology term. The carrying capacity of the environment has been reached.